Ever notice how a steaming cup of coffee like seems to hold this like universe of energy,
Yeah.
at least, until it cools down. Today, we're taking a deep dive into the very laws that, dictate that energy transfer, the laws of thermodynamics.
And not just coffee, right? These laws, they underpin, well, everything from like the largest stars to the smallest atoms. It's incredible.
Yeah. It's like having a backstage pass to, how the universe actually operates.
Mhm.
We're using Peter Atkins's book, Four Laws That Drive the Universe, as our guide. And he starts with this almost deceptively simple um, concept of temperature. We all know what it is, sure. But have you ever, like, stopped to think about what it really measures?
It's a deeper question than it seems, at first glance. I mean, we use a thermometer, yeah, but what are we actually quantifying there? The answer is thermal equilibrium. It's that point when two things in contact stop exchanging energy as heat.
Okay, so my hand and say, that coffee cup, eventually, like, they hit this equilibrium, neither one getting hotter or colder.
Precisely. And that seemingly simple observation, it actually leads us to the Zeroth law of thermodynamics. It states that if two systems are each in thermal equilibrium with a third system, they're also, get this, in thermal equilibrium with each other. This almost obvious truth, it underpins our entire concept of temperature as we know it.
It does seem kind of self-evident when you put it that way. If A equals B and B equals C, then A equals C, right? But I never really thought about that applying to heat and energy on such well, a fundamental level, I guess.
It really is remarkable, isn't it? Like the foundation upon which all the other laws they're built. And it allows us to think of temperature as this universal property, not just,
Yeah.
a measure of how hot or cold something, feels to us subjectively.
So temperature isn't just about our senses. It's an actual, like, a fundamental property of the universe itself. Mind-blowing.
Exactly. And when we dig a little deeper here, we see that temperature is, at its core, a measure of the average speed of the molecules within a substance. Think about that hot coffee again, those molecules, they're just vibrating faster. That's all it is.
That's incredible. It's like all those tiny molecules are like, doing this incredibly fast, energetic dance. And the faster they move, the hotter it feels to us. So when the coffee cools down, those molecules are basically just, what, calming down their moves a bit.
Precisely. And this understanding of temperature as molecular motion, it becomes even more important as we delve into the other laws, um especially the first law, because well, it throws a bit of a wrench into our human desire to, well, get something for nothing.
Oh, yeah, I was about to ask. If energy is just molecules moving, could we, like, I don't know, build a machine that perfectly captures that movement, like a perpetual motion machine or something?
That's the dream, isn't it? A machine that just keeps going and going. Unfortunately, that's where the first law of thermodynamics, well, it steps in to say, not so fast. Just like your bank account has a balance, so does the universe's energy budget. This law states that energy can neither be created nor destroyed. It can only be, transferred or transformed from one form to another.
I'm sensing a theme here. No free lunches in the universe, huh? But okay, if it's just transfers and transformations, that means, like, in theory, we should be able to perfectly track where every bit of energy goes, right? Like, follow the bouncing ball.
In a closed system, absolutely. But we need to make a distinction here between two main ways that energy moves: heat and work. Heat is energy transfer driven by a difference in temperature. Think of a hot stove burner heating up a pan, right? Work, on the other hand, involves the ordered, uniform motion of atoms, like a piston compressing a gas, for instance.
Okay, so heat is more like a free-for-all of energy transfer, while work is more organized, more intentional. Like the difference between a mosh pit at a concert and, like, a synchronized swimming team.
An apt analogy. Both involve a lot of energy, yeah, but they are channeled in very different ways.
And in both cases, though, we're still just talking about those tiny little molecules changing their state of motion, right? Like when I burn um, gasoline in my car, for example, that's a whole lot of molecular activity going on under the hood, right?
Absolutely. Burning gasoline, what it does is it releases the chemical energy stored in the fuel as heat. This heat, in turn, then does the work of, well, making your car move. It's a beautiful cascade of energy transformations, but it all happens within the bounds of the first law. No energy is created or destroyed, just, transformed from one form to another.
So the first law is like the cosmic accountant, making sure the universe's energy ledger, it always balances. But if energy is never truly lost, just transformed, why does it feel like things always get, I don't know, messier? less organized over time, like my desk after a long day of work. This is where the second law comes in, right?
You're absolutely right. Things, they do tend towards, well, disorder, don't they? The second law of thermodynamics, it doesn't let us off that easy. Even if the total amount of energy stays, stays constant, your desk after a long day, it's a perfect illustration of this law in action.
So there's like a cosmic force out there pulling for more, more mess, more chaos in the universe.
In a way, yeah, you could say that. It all boils down to this concept of entropy. Think of it as a measure of how dispersed energy is within a system. So the more spread out it is, the higher the entropy. Your tidy desk, for example, with everything in its designated spot, that's low entropy. But papers scattered everywhere, coffee mugs askew, that's high entropy in action.
So the universe, it prefers my desk looking like a disaster zone. That's oddly comforting, actually. But if it's all about energy spreading out, how does that explain, how do you explain life itself? Life seems to be the opposite of entropy, right? Creating order and complexity where there wasn't any before.
That's the beauty of the second law, isn't it? It sparks some of the most profound questions in science. The key here is that while the total entropy of the universe, it always increases, right? There can be localized pockets where entropy decreases, where order emerges. But that order, it always comes at a cost, you see.
So it's like borrowing from the cosmic entropy bank, and you always have to pay back with interest.
That's a fantastic analogy. Every time your body, it uses energy from food to build new cells, to create order, it releases heat, right? And that heat, it increases the entropy of the surroundings more than the decrease that happened within your body. So it's this cosmic balancing act, you see.
And this balancing act, it has some pretty big consequences, even for everyday things. You mentioned refrigerators earlier. How does a fridge, a machine that's literally designed to keep things, organized and cold, how does that obey this second law? It seems counterintuitive.
Refrigerators they're a fantastic example of how we can locally reverse entropy, but only by putting in work, by using energy, right? A fridge, what it does is it uses energy to move heat from the cold interior to the warmer surroundings. This transfer, it doesn't happen spontaneously. It requires a pump, usually driven by electricity, to force that heat against its natural flow.
So my fridge is like this tiny little rebel fighting against the universal tendency for disorder. That's strangely inspiring.
It is, and the more efficient your fridge is, the less energy it wastes, the less it contributes to that overall increase in entropy, you see. The second law, it kind of sets this efficiency speed limit for us.
So we can't win against entropy, but we can play a smarter game.
Yeah.
What about other machines like car engines? Do they bump up against this entropy ceiling too?
Absolutely. Heat engines, like the one in your car, they work by converting heat into work, right?
Right.
But the second law, it tells us that this conversion, it can never be 100% efficient. Some energy is always lost as unusable heat. And that increases the overall entropy, you see. There's this fundamental limit to how much work you can actually squeeze out of a given amount of heat.
That sounds like a challenge to me. Are engineers constantly trying to build more and more efficient engines to get around this, to beat the system?
They are. And they've made some truly remarkable progress, but there's a fundamental limit there, a point you just can't get past no matter how clever your design is. A brilliant French engineer by the name of Carnot, he figured this out back in the 19th century. He showed that the maximum efficiency of a heat engine, it depends solely on the temperature difference between the heat source and the cold sink.
So a hotter engine and a colder surrounding environment would be more efficient. Is that what he was getting at?
Precisely. But even then, there's a limit there. And it's because of something incredibly mind-bending, the concept of absolute zero, the lowest possible temperature. And that, my friend, brings us to the enigmatic third law of thermodynamics.
The ultimate limit. even more fundamental than my desk's natural state of disarray. I'm ready. Tell me more.
Yeah.
Okay, so we've got this concept of absolute zero, the ultimate cosmic chill.
Mm-hmm.
Is it like a temperature black hole or something? Impossible to reach, let alone escape from.
It's a fascinating analogy. The third law of thermodynamics, it throws down the gauntlet, you see, and says, look, you can get arbitrarily close to absolute zero, sure, but you can't actually reach it. Not in a finite number of steps anyway.
So even with like all our technology, all our scientific understanding, it's still kind of like a cosmic brick wall we just can't break through. What's the reasoning behind this ultimate limit? Why does it even exist?
It's deeply, deeply connected to that, the very nature of entropy itself. Remember how we talked about entropy being a measure of disorder? Well, the third law, what it implies is that at absolute zero, a perfectly ordered crystal, it would have, well, zero entropy. Every single atom would be, in its designated spot, completely still, with absolutely zero possibility of any randomness whatsoever.
That sounds, well, incredibly serene, actually, like the universe achieved like perfect zen or something.
Hmm.
And also kind of, I don't know, lonely, no movement, no possibility for change. Is that even theoretically possible?
It is purely theoretical, of course, this state of perfect stillness and order, but the implications of even just approaching absolute zero, those are far from boring, let me tell you. It's a realm where materials, they start to behave in truly bizarre and fascinating ways. We're talking superconductivity here, where electricity, it can flow with, get this, zero resistance.